All right, everyone, and welcome to our last moment of inertia focused lesson. So we're going to go through some odds and ends as well as learn how to do this, because finding the moment of inertia of a system is going to be a requisite part of the harder problems in chapter 10, sort of like a baseline skill. So we've got to make sure that we're really on it. So to recap, I, for a bunch of point masses, is just going to be the sum of the mr squareds. I, for a stick, about the COM, 1/12 ml squared. I, hoop, COM, mr squared. I, disc, COM, 1/2 mr squared. I, solid sphere, COM is equal to 2/5 mr squared. So that's the basics here. We also had the parallel axis theorem. I through a parallel axis is equal to ICOM plus md squared, where m is the mass of whatever you're applying the parallel axis theorem to, d is the distance between those two parallel axes. And then we had I perpendicular is equal to Ix plus Iy, and that was the perpendicular axis theorem. Sometimes this is called Iz, which this is the moment of inertia through the plane of the rotating figure, and these are two axes that are perpendicular and in the plane of the rotating figure. So I want to do a couple of applications of this stuff and look towards what are called composite systems. So first, I have a coin. A coin is a disc, yes? And so if I were to rotate the coin like this, about an axis that goes through its center, that would be 1/2 mr squared. But this is not how we normally rotate a coin, is it? We normally rotate a coin, whoops, like that. So let's talk about how we can find the moment of inertia of a coin like this, and then we can kind of see how we can extrapolate that outwards. So if you think about that, just to draw it, here's my coin. When I'm rotating it like that, I'm rotating it about an axis like this. Now, I happen to know what the moment of inertia is through an axis that goes through the coin like that. So what we can use here is the perpendicular axis theorem, because if I rotate the coin about that axis, that's like this, that would be identical to rotating it about that axis, which I also don't know, right? So here's my Ix and here's my Iy. The thing is, Ix is going to equal Iy because of symmetry, but I know that my I perpendicular here is going to equal 1/2 mr squared. So using my perpendicular axis theorem, I can see that I perpendicular is equal to Ix plus Iy, which would be 1/2 mr squared is equal to essentially 2 times either Ix or Iy, meaning a coin rotated in that way would be 1/4 mr squared. And so that's a way we can use the perpendicular axis to take something that's very easy to know and turn it into something that's a little bit harder to know, because the integration here for this would be really difficult, because individual, like if this was the axis of rotation, individual bits of mass here would have different radial distances as a function of where along this axis it would be, and that's a very difficult integral to set up. And we want to avoid setting up difficult integrals when we can use symmetry and our rules to our advantage. So let's look at that through another perspective. So this piece of paper is a rectangle. I know, not a shock there. What happens if I wanted to rotate a piece of paper like this? Well, I know it's sort of weird to think about, but if we look back to the moment of inertia of the stick, when I did that, I just drew this little segment of mass there. Notice all that mattered was the distance to that from the axis of rotation. If you think about it, a sheet of paper is just a wide stick. The length of this little dm didn't matter. Therefore, if I am rotating a rectangle about an axis here through its center of mass, that I, for a rectangle, let's say that the side of the piece of paper is, A, then that just would be 1/12 the mass of the paper, A squared. It just functions like a stick of length A. And if I were to rotate about, I don't know, this, where here's the side is B, I of the rectangle would just be 1/12 MB squared, right? And so then what would it be if I were to rotate the piece of paper through here like that? Well, once again, that'd be the perpendicular axis theorem. So I perpendicular for a rectangle through an axis through its center of mass would just be 1/12 MA squared plus 1/12 MB squared, which is just 1/12 MA squared plus B squared, right? And that's for a rectangular piece of paper through its center of mass through the plane. Okay? So I can use my perpendicular axis theorem and my notions about these derivations to figure out more complicated systems. Now, what happens when we have a more difficult system composed of other things? For example, let's say I have, in the classic example here, a grandfather clock. A grandfather clock is going to rotate like this. It's going to rotate, say, about that point. And this is like a pendulum going back and forth. And this, let's say it's a disc, right? So this is a disc, and we'll make the disc of length R and mass, I don't know, let's just go MD. And here's my stick. Let's say my stick is 5R long, right? And let's say the mass of the stick is MS. Why don't we make this easier? Let's say the stick is a mass of M and the disc is 4 times what the stick is made out of. And I want to know the moment of inertia of this system about here. Oof, well, how do I do this? Well, essentially what we're going to do is see that if the moment of inertia of a series of point masses is just the sum of the moments of inertia of each point mass separately added together, then the moment of inertia of a system is just going to equal the sum of the moments of inertia of the parts of the system. So in this case, mass of the eye of the stick plus eye of the disc. Now, here's the thing though. Notice that neither the stick nor the disc are being rotated about their center of mass. So I'm going to have to apply the parallel axis theorem individually to each. So I of stick is just going to become I COM of the stick plus mass of the stick times the shifting factor for the disc, for the stick squared, right? And then separately, I COM for the disc plus mass of the disc, d for the disc squared. So notice here, before I had a mass total there. That was because I was applying the parallel axis theorem to the total system, whereas here I'm applying it differently for each, because if you notice the shifting factor for the stick is going to be different than the shifting factor for the disc. So what does this look like? Well, ICOM of a stick is 1/12 ml squared. Well, the mass of the stick we said is capital M. The length of the stick is 5R, okay? The mass of the stick is M. How far is this shifted over? That's going to be 2.5, R squared, because that's how far where I'm rotating the system about is from the center of mass of the stick, plus, and now a disc, which is 1/2. Well, mass of the disc is 4m. The disc's radius is r, quantity squared, plus mass of the disk, 4m. The shifting factor, so let's say that's 5r, 6r quantity squared, and there you go. And then we can just kind of put this all together. So this first term becomes 25/12 mr squared. The second one, 6.25 mr squared, plus 1/2 of that, that's 2 mr squared, and then plus, well, 36 times 4, 144 mr squared. And then I can find a common, actually, usually what's best for this is to find some sort of common denominator and put it here as a fraction rather than have any sort of compound number or decimals. We're gonna see that that's going to be very helpful for our problem solving later. So this is 25/12, and this in terms of twelfths. So this would be 25/4, yes, 25/4. In terms of twelfths, 375 twelfths mr squared. 2, that's pretty easy, that's just 24/12 mr squared with 144 times 12 over here in the corner. 8, 2, 8, 4, 4, 1. That's some sort of ridiculous number, but 8, 2, 7, 1 twelfths mr squared, and then we can put all that together into one number. It's not really relevant what that number is, but there you go, and that would be the moment of inertia of that system. So there's going to be a worksheet posted with a bunch of different compound systems, and the assignment that will go with that will be delineated. It's not going to be all of those problems. I'm just going to give you a couple of them, and then I'll post a solution set for those, and then you can post your responses so I can check over your work. Notice here, setting up the initial idea, showing what each of these, sometimes you don't have to do the parallel axis theorem. Like for example, if I rotated this system about an axis through the center of the disk, I would just be using I of the disk, would just be ICOM of the disk, and there'd be a parallel axis theorem for the stick. It all depends on what the problem is. But we'll work our way through it. Okay, thank you.